Hello there, welcome back. We continue with mutation testing. Last lecture I introduced you to what mutation testing was. We saw some basic definition. I'll just briefly recap that. Mutation testing involves taking a program which we call a ground string and applying one of the chosen mutation operators at a particular time to get a resulting program which we call a mutant. Mutant should be a syntactically valid program, compilable, and then the goal is to write test cases, run the ground string on the test case, run the mutant on the test case, observe if the outputs differ. If the outputs differ, then you say the test case kills or strongly kills the mutant. The other option is weak killing, where the output or the state of the program is different at the place where you apply the mutation. So this is the basic concept of mutation. Mutation operators, plenty of them are available for several different common programming languages: C, Ada, Java, Fortran, Lisp, C++, and so on. There are tools that are available that let you do mutation. Basically, for each programming language, mutation operators are available at the unit level, which lets you make low-level changes to individual statements in the program, like changing a less than or equal to less than in terms of relational operator, changing plus to minus in terms of an arithmetic operator, replacing variable references, and so on. You can also mutate at the level of integration testing or call interfaces, where we could change a procedure call, a function call, by changing the arguments that are passed in the call, by mutating the place where the call is made, the location where the call is made, by removing the call and replacing it with an appropriate return statement, and so on. So mutation operators are available for different programming languages at the unit level to make statements to to make changes to individual statements, and at the integration level to make changes to call interfaces. Mutation operators are also available at the level of specification languages, like those that are used for model checking, like SMV. Mutation operators are available for popular input markup languages like XML. They are available for SQL, and so on. Almost all these languages have similar looking mutation operators, the one that change one kind of relational operator to the other, one kind of arithmetic operator to the other, and so on, at the unit level. At the integration level, they might differ based on the features offered by the language. As we discussed in the last lecture, what is the goal of mutation testing? To make one change somewhere in the program and see what the resulting behavior is. The resulting program becomes a mutant, and by writing a test case that kills the mutant, we could make some inferences about the program. So mutation testing is typically done to isolate a typical mistake that could be made by a programmer, otherwise done during debugging the program. And mutation operators are designed to mimic programmer mistakes, typically replacing less than with less than or equal to, or greater than with greater than or equal to, changing array indices, changing variable references, and so on. The other thing testers are commonly supposed to do is that suppose your code has scope to get into an operation which involves a division by zero, which is illegal in mathematics and in computer science. So typically a developer, as a part of routinely debugging his or her code, should test the code for these kinds of errors. So mutation operators like fail on zero are designed to encourage developers to do routine testing practices. So typically mutation operators, if you take for a programming language like Java, is available. Large set of mutation operators are available, hundreds of them, but we don't use all of them. We will walk through the list of all the mutation operators at any point in time based on the need of a programmer or tester. A particular part, a statement in the program is mutated and tested. And along with that, tests have to be created to kill the mutant. So you might ask, if there are so many mutation operators available for a programming language at the unit level and at the level of call interfaces, how do I know what is good and what is bad? Mutation operators, when are they considered to be effective? Typically, people write test requirements to say that these are the mutants that you should do. And if I'm able to mutate and kill all the resulting mutants, let's say 7 different mutants are expected to be created and tested, and I'm able to do, let's say, 6 out of those 7, then that effectiveness is measured by saying, okay, this is your score. This is how much you have done. Otherwise, we don't have any other concrete measure to see whether mutation operators have been effective or not. So what we now do is, in this lecture, I'll provide you what we call program level or unit testing level mutation operators for a programming language like Java. Because it's at the unit level, there are no specific features. You could use it for several different programming languages, or because all of them will have arithmetic operators, relational operators, logical operators, and operators like plus plus and so on. So at the unit level, they apply to several things. In the next lecture, we will see at the interface level. So now what we do is to look at a reasonably exhaustive list of mutation operators at the unit level. It's an exhaustive list. We will go over the list one by one patiently. But please remember, this is meant to give you an indication of how many different mutation operators are available. You need not use even 3 or 4 of them at any point in time. As a tester, maybe you will have the need to use 1 or maybe 2 of these kinds of mutation operators. But it helps to know how many different operators are available at any given point in time for a programming language. So we will look at the unit level mutation operators now per slide, and there are quite a few slides that we're going to see. The first kind of mutation operator is what we start here. So suppose we had an arithmetic expression. If you look at this last bullet here, it gives you an example. So you had a statement like x is equal to 3 into a as a part of the code of your method or your function. Maybe the programmer intended to write x is equal to minus 3 into a, or x is 3 into minus a. We don't know. So there are mutation operators that modify arithmetic expressions by inserting absolute value. So each mutation operator, each arithmetic expression or a part of an expression can be modified by inserting functions like ABS, stands for absolute value, negative ABS, neg ABS stands for the negation of the absolute value, or by inserting functions like fail on 0, which tests whether the value of the expression is 0. If the value of the resulting expression is 0, then the mutant is killed, otherwise it's ignored and the execution of the program continues. So as an example, suppose we had a statement like x is equal to 3 into a. You can mutate it to create something like x is equal to 3 into absolute value of a, x is 3 into negation of absolute value of a, x is fail on 0 of a, and so on. So this absolute value insertion is one small set of mutation operators that are available. Next kind of mutation operator is what we call arithmetic operator replacement. Usually, if you carefully read this term, one will be given per slide, that is given in blue color, you will get to understand what is the kind of mutation operator we are talking about. So arithmetic operator replacement. So it says take one kind of arithmetic operator and replace it with other. So suppose I had an expression which uses one of these lists of arithmetic operators, plus, minus, star, slash, exponentiation, and so on. I can replace the occurrence of one with the other just to check if maybe the programmer intended to do one operator versus the other. In addition, I can also do these special kinds of mutation operators, like each arithmetic operator is a binary operator, right? So it has 2 operands, a left operand and a right operand. So there are special mutation operations that helps us to retain only the left operand or only the right operand, or modulus, which computes the remainder when the left operand is divided by the right, and so on. So for example, suppose I had a statement x is equal to a plus b. I can use arithmetic operator replacement, replace this single arithmetic operation that I see here, plus, with the other kinds of arithmetic operators. I can replace plus with minus to create x is equal to a minus b, or plus with star to create x is equal to a star b, or with slash to create x is equal to a slash b, or with exponentiation, or just retain the left operand and keep assigning x to a. A to x, or retain the right operand, assign b to x, and so on. So arithmetic operator replacement is another kind of unit level mutation operation that we can apply. Similarly, you could do a replacement of relational operators. Relational operation replacement. Each occurrence of a relational operator, what are the various kinds? 6 of them are there. Less than, greater than, less than or equal to, greater than or equal to and not equal to. They can be replaced one with the other, or you could replace the whole relational expression with the Boolean constant true or the Boolean constant false. So that's this false op and true op. They are special kinds of mutation operators. Again, for example, if there is a statement of the form if m greater than n, this involves a relational operator greater than, I can mutate this to create several different mutants by making that if m greater than n, take the greater than, replace it with greater nor equal to, less than, less nor equal to, not equal to, or just retain true or retain false. Any of them I can do. Sorry, there's a typo here. This one should be not equal to, if m not equal to n, the last one here. Similarly, the next one is if I have logical operators or conditional operators and or not, I could take one, replace one with the other. Again, wherever the logical operators are binary in nature, I could retain only the left operand or only the right operand. So for example, if I had if A and B, and is the logical and, conditional and, then I could replace this and with or, with a single and, with a single or, with XOR, or retain only false or only true, or retain the first operand or second operand. So this is conditional operator replacement. Similarly, sometimes I might use shift operations, left shift, right shift. So each occurrence of the shift operators can be replaced by the occurrence of the other operator, or I could just keep the left operand. So for example, if I had shift x is equal to m shift a, I could mutate it to create these variants. Similarly, if I had a bitwise AND and a bitwise or a bitwise XOR, then I could replace one with the other. Here again, because these are binary operators, I could retain the left operand or the right operand standalone. So this is logical operator replacement. Then I can have assignment operator replacement. Suppose I had statements like x plus is equal to 3. I could replace plus equal to with minus equal to, star equal to, just equal to, and so on. So many different operators are possible. This is assignment operator replacement. Similarly, if I could insert a unary operator like a negation or a conditional or a logical and so on. So suppose I had x is equal to 3 into a, I could write it as x is equal to minus 3 into a, 3 into minus a, and so on. So I could delete unary operators. Like for example, if I had if a greater than minus b, I could delete the minus to create if a greater than b. Or I could add the minus here, like unary operation insertion, unary operation deletion. I could replace one reference to one scalar variable with the other. Please note this excludes pointers. That's why I've used the word scalar variable. So you can't apply this for arrays and lists and so on. Each variable reference is replaced by each other variable of the appropriate type that is declared in the current scope. So if I had a statement x is equal to a into b, this is mutated to create x is equal to a into a. I could replace, there are three variables, x, a, and b. I could replace one with the other and create all kinds of variants. Several of these variants are possible by replacing one variable reference with the other. We saw this bomb statement last time when we looked at mutation testing. So I could take a particular statement. I am not allowed to delete it because we don't delete statements when we apply unit level mutations. We either replace individual operators in the statement or we replace this statement with a bomb statement which signals a runtime failure when we reach that statement. So it's useful for testing reachability of a statement. The word bomb may not come as it is. When you use a mutation tool, it could be replaced with an appropriately indicative term. So what did we do across all these slides? We saw an exhaustive list, reasonably exhaustive list of mutation operators. So in general, if you have a method or a function that has a few lines of code, right? In that, take a particular statement. In that particular statement, you could use any of these kinds of mutation operators that we saw. If that statement has an arithmetic operator, replace arithmetic operator if you suspect that that's the statement that you want to test for. The statement has a relational operator, then you could replace the relational operator with the appropriate other operator that you want to test for. You could change variable references. So these are absolute low-level, unit-level operators that are available as a part of the mutation testing tool for almost all standard programming languages. So you could try it out based on the place that you want to mutate, the statement that you want to mutate, and what would be the reason for you to mutate that statement, because you suspect that there is an error with the use of a particular operator in that statement. So you mutate it appropriately. The list that we saw is reasonably exhaustive, right? But remember, we're not going to use all of them, definitely not. It's just meant for you to know how many different mutation operators are present at the unit level, so that based on your need, you could use them as needed. So I'll stop here for now. In the next lecture, we will look at mutation operators specific to integration testing, call interfaces. Thank you.